Good morning, good afternoon, and good evening, everyone. Welcome you all to this webinar co-hosted by ACL Digital and Delatech. The focus of this webinar will be primarily to understand the role of AI ML in the overall O-RAN Fronthaul deployment and specifically talking about the benefits and the challenges. So we would be going over what we see in the industry today, how do we kind of see the AML playing a larger role, and then talking about some of the deployment challenges and the benefits. So we'll take you through the complete session today and look forward to have a active participation as we go forward. So as part of the introduction, as part of the agenda, there are key areas that we're planning to cover. One is definitely the industry today, how they are looking at Open RAN and the problem that we see with the typical Open RAN deployment that we see in the industry today, and how we can solve by leveraging AI ML as a solution in the overall ecosystem is what we're going to talk about. And we have industry expert coming in, and we will have a kind of a Q&A session, which kind of takes over the entire discussion and clarify any of the questions that we come across in this overall discussion. Can we go to the next? Yeah. So as part of the speaker list today, we have two distinguished leaders from the industry. Ganesh Shenbagaraman from Radisys, who heads the standards and regulatory affairs for Radisys. And we have Balaji Raghunathan. He is heading the 6G practice and he's the Chief Technology Officer for Keysight. And we have Rajesh Rasalkar, co-founder for Delat, Vignesh Manohar, CEO for Delat, and Hari heads the O-RAN system engineering for Delat. So that these are the speakers for today. We talked about it at a high level in first initial slides, but again, just covering up that. The first initial part would be talking about the Open RAN as an ecosystem and the challenges that we see. Then we'll talk about the AI-enabled Open RAN, which kind of solves a couple of challenges that we have kind of highlighted. And then in the last few slides, we'll talk about how it is going to evolve as we move across 5G and then to 6G. So that is going to be the theme for today's discussion.
Hey, thank you, Arunesh. Good morning, good evening. This slide just provides the overview about Open RAN, or you can call it O-RAN architecture. And as many of folks on this call know, actually, the O-RAN architecture brings flexibility, cost benefits by by decoupling the hardware and software components, correct? And it also offers vendor interoperability once you do the split. O-RAN, as we know, the RAN disaggregation have been gaining a lot of momentum, correct? I think there are a lot of announcements from both operators as well as from equipment vendors. And the O-RAN architecture has been extensively discussed in the context of 6G. So within O-RAN, correct? So Open RAN or O-RAN 7.2's functional split is a key architecture choice in O-RAN. That defines like how the radio units and the distributed units can interact, correct? So it divides the base station which is a G node B in 5G into a functional components to optimize the cost, the performance, and also the flexibility. Within 7.2 split architecture, the RU and DU, they communicate over the open fronthaul interface, typically based on the eCPRI standards. So today's talk is more about like to discuss some of the challenges and how the machine learning can be used to solve these challenges. And as you know, there have been a lot of advantages with O-RAN deployment, but however, because of this open fronthaul interface, the 7.2 split uh, between the DU and RU has been very complex topics for the discussion as well as for the implementation. And there are multiple challenges. I think one of the big challenge is also the interoperability of the O-RAN alliance specifications on this open fronthaul. When we talk about like DU and RU coming from different vendors and they have to manage like the thousands of profiles, correct? Just to get this interoperability and open fronthaul to work properly. But I'm going to invite, I think, Ganesh and Balaji, who are industry experts, to talk about some of the technical as well as some of the standard challenges on this open fronthaul. Can you go to next slides? And yeah, let Ganesh and Balaji take to talk about some of those challenges here. Hey, Ganesh, we cannot hear you. You're on mute.
Sorry, yeah, I would go first, sorry. And let me talk quickly about the deployment challenges, and Balaji would also add his perspectives from a standardization perspective as well. So the flexibility which Rajesh just talked about in flexibly deploying in different configuration and topologies, that's the strength of this deployment of the standard. And it comes with all the performance demands. Let's say when you deploy different configurations of radios, 4T, 4R to 88R to 32TR or even 64TR, managing the performance of all these radios, meeting the performance requirements, and the topology as the network scales, it brings its own set of complexities and challenges. And as the network scale or an deployment scale, we're going to see more challenges coming from the transport or a timing or purely from the RAN domain aspects. So there are ways to solve it. The standards are very versatile and giving you multiple options, but the same versatility and flexibility gives you enough complexity in the sheer permutation and combination of parameters, both on the DU side and RU side, especially when you talk about multiple RU vendors and multiple DU vendors, true multi-vendor environment, then this is going to be a challenge in managing the network and deploying the network at scale.
Okay, maybe I can talk a little bit about the standards aspect. So as we all know, O-RAN started as XRAN, and it actually carries some of that history still today, in the sense that the original specification was mainly around the front haul in the XRAN days, but as O-RAN, there are more interfaces that have been added, including the RIC interfaces, and even the SMO aspect. So this has created certain complexities. For example, the RU has an M plane, which is different from the management plane for the other modules at the moment. But beyond that, I think the standards, overall has been widely participated, and now you have a very large number of players, participating in the O-RAN standards process, but also the derivative aspects of the test and certification. Using the so-called OTICs, O-RAN Test and Integration Centers, has also been, and I would say, an innovation, but also very useful in terms of bridging the gap between the standards and the actual deployability. And you can see that in the initial days, where it took many weeks to get interoperability between a DU and RU. Now, I think we can basically achieve it in a very short period of time, at least the basic interoperability. But still, lots of challenges are still being worked on, and the standard is still evolving. These include the shared RU support, the uplink performance optimizations, and most recently SRS-based beamforming work items. So as the specification in 5G evolves towards 5G advanced and into 6G, we will see corresponding optimizations and enhancements come through in the fronthaul specification as well.
Rajesh, you have anything to add before I take over?
Yeah, just quick. As Ganesh and Balaji has mentioned, I think open fronthaul presents the good technical challenges, but I think, however, like with proper planning, like synchronization, bandwidth optimization, I think these challenges can be addressed, correct, for large scale deployment. And I think for today's discussion, I think this is what we are going to explore, how the Dallar's platform can be utilized, correct? We utilize a lot of machine learning. The platform utilizes machine learning using some pre-trained configuration, using some kind of a graphical neural networks, which is based on the deep Q learning. But I'm going to introduce Hari and Dr. Vignesh. They're from Dallar technical team to provide further details on the ML implementation. So go ahead, Hari and Vignesh.
All right. Thank you, Arunesh. Balaji, Ganesh, Rajesh, for your insightful thought leadership. I mean, good morning, everybody. I'm Hari, and I'm very excited to have the opportunity to speak with you today. Right. I think the problem statement, what we are going to look closely today on this webinar is a front hall focused. And also, I think specifically the topology and how we're going to basically, automate the whole of this deployment or operations. So I guess on the previous slide, the Balaji and Ganesh has said, we have predominantly LLSC1 topology that's being currently followed for greenfield deployments. That is okay. But as we scale into brownfields and also into our dense urban networks, right, we need to actually adopt LLS3C3 topology. So I think what I'm going to basically talk to start with is, primary C3 topological deployments that have happened today, where what you predominantly see is operators deploying low-cost, mid-range COTS DU platform and also low-end switch to manage bunch of radios, basically up to 6 radios. That's the trend you would see today. This actually has a huge effect on the cost because, to manage just 6 radios, you're dedicating a complete DU platform, which is quite expensive, and also a dedicated switch. It's not by choice, but it is mostly by, they are forced or obligated to choose this kind of setup. This clearly is an expensive, unscalable, setup what we have, and it's under provision network to say the least. Okay, so this model basically unsustainable both from capital spending and also from operational expenses standpoint. Can we go on to the next slide, please? We broadly divided motivation into 4 categories. We talk about efficiency part first, which is the key driver for whole of the engineering work that we are doing at Delart in collaboration with ACL and also Radisys. The efficiency part, if you look, what we have today is about 20K DU platform with a 10K front hall switch managing about 6 radios, which translates to about 5K cost per radio to connect to a front hall. However, we have on the market, off the shelf, high-end DU platforms that are about maybe 70K in cost, which can provide a lot more compute and networking capacity. And we have front hall switches that offer almost 2 to 4 terabytes network processing capacity. If we bring those two things into the front hall network, we could pretty much connect hundreds of radios to one single COTS DU platform. We're going to basically see these details later in the webinar. However, I think that's the key efficiency part that I want you all to basically, look forward to improve the flexibility of O-RAN front hall networking, both driving automation part and also improving efficiency part for the operations. The next driver for us is the availability. If you look at how the RAN networks were managed by the incumbents, they have set a certain benchmark. So which is, there is that 99.9% availability or 0.99% availability. The O-RAN to start with has to meet those numbers. This is a key challenge. If you look, the split has brought in flexibility, open interfaces. We can mix and match solutions, pick the best of breed. However, the critical challenge is getting to the problem right away and fixing it so that our availability of the service is 99.99. However, that 99.99 actually translates to just few hours of downtime per year, so which is very, very stringent. The other aspect we actually want to talk about is the scalability part, which is the C1 deployments. They work for greenfield deployments. However, they don't really provide meaningful solution to brownfields and also urban. And we have, moreover, I guess, this industry acknowledges there are hundreds of combinations for interoperability and thousands of parameters, 10,000s of parameters to configure, identify, troubleshoot, get to a problem. So what is being currently followed is a brute force approach, even for provisioning and also for most of the, the service offerings that operators are doing today. So this is where I think we looked at few critical use cases to start with, most critical use cases, where AIML can come in and provide real-time network state for provisioning and maintaining the network. We can move on to the next slide, please. We have pretty much under-provisioned network using low to mid-end hardware delivering brownfield deployment services today. However, I think we have to move or transform fronthaul network significantly at the same scale as data center in order to actually drive meaningful revenue for the operators. So what we are looking at as a key theme for this webinar is, you see that center, the transformation, two aspects, critical aspects, the telemetry, more and more use of telemetry, that's a large data, RAN analytics, it's barely mined, it's a huge data mine. So these two are key sources for our ML algorithms to learn thresholds, to learn about deploy global models that can help accelerate the deployments. So, to basically summarize, what we are saying is an operator going with a 80K and 30K switch combination can deploy hundreds of radios in the field, which will bring down eventually everything like CapEx, real estate costs, power bills. Capacity is going up significantly, 6 to 8x. Can we go on to the next slide? So before I hand over to Dr. Vignesh, I would like to actually highlight few things here that is going to set the tone of the data gathering part. I think we understand fronthaul is very complex. It's very time-sensitive network, huge bandwidth. And then we have hundreds of profiles coming from each of these components like DU and RU. Right? You see that there is a list of profiles supported by each of these components. And eventually operator is looking at enabling or selecting the desired profiles from this list based on his use cases. Actually, if he wants to deploy 20 megahertz carrier, so he's looking at typically one of those configurations. So what is my subcarrier spacing? He's looking at another tick point there. And then he's making he needs to make those selections. And then eventually this set has to interop over a complex network. And then it's not quite straightforward or easy. It's more often than not, the engineers are doing like a brute force approach to find a sweet spot where the things start working, they can interrupt. So the key is, out of all the different traffic kinds that get exchanged on the fronthaul, the quite easiest part or the easiest traffic type to interop is management plane. I think from day one of the specifications, the standards have thought about zero-touch provisioning, wherein you power on the DU or radio, they're supposed to do a call home, and then exchange capabilities. And pretty much the management entity has an idea of how the network should present itself so that these can interop and deliver meaningful services and perform better. So the management plane aspect, which is already thought, standardized, zero-touch provisioning should let a distributed entity, central entity, rig platform, or some agent in the front hall collect the profiles, and then we could basically go over that and come up with likely use cases, selections, and put through the front hall, apply front hall limits to derive network topology that can optimally work for, or that can meet the latency requirements of both DU and RU, basically in uplink and downlink direction. So, and that should drive the cost lower. So with that, I would hand over the talk to Vignesh to go over the results.
Yeah, thanks, Hari. Nana, can you stay on the previous slide? Yeah, thank you so much, everybody, for taking the time out to attend this webinar. I would just like to remind everybody that please use the Q&A section at the bottom of your screen and put all your questions there. Keep them coming, and we'll do our best to answer all the questions to the best of our capabilities. So we really look forward to all your questions. And coming back to the topic, just as Hari explained, the front hall is an extremely complex entity, and we're actually looking at a deployment of hundreds of RUs, which would be connected to a single DU. Each RU can have multiple profiles, right? And so these, as even Ganesh pointed out, like these kind of combinations results in thousands of combinations, right? Permutation and combination wise, which we have to meet the requirements of which have to be met so as to have successful communication between DU and RU. Now, typically, what has been done is more of a brute force, kind of engineering technique, where we take all these profiles, we have the latency requirements, we know the DU, we know its latency requirements, and we try to mix and match in our own way, which takes a lot of time and engineering effort. And this is where we are bringing in the notion of ML into the life of operators, so as to make this entire life simpler, so that we can design this interoperability and design the front hall in a very quick and an efficient way. So now, if you look at the table below, right, this is a data set that we've been able to create synthetically. It is synthetic in the sense that we don't have live data from operators, but it's not false data. It is still very representative of the kind of numbers you would see on the field. And immediately you can see that for one RU, there are so many profiles, only 14 are listed here, but the actual sheet actually goes much beyond it. You can see different bandwidths, you can see different downlink frequency, uplink frequency, etc., etc. Out of all this, we are concentrating only on the latency min and the latency max requirement for each RU for this webinar. There are efforts already ongoing within our company to actually process a diversity of these requirements, right? So you can look at so many different other latency requirements, this TA3 max, TA3 min, etc., etc., right? So we can take all of that also into our processing. But for this current webinar, we are just concentrating only on the min and the max latency requirement that enables the DU and the RU to talk to each other. With that, I go to the next slide, which will detail the ML framework in which we're operating. So the key for us is reinforcement learning, which is actually a learning or a type of machine learning where the algorithm learns from the environment it operates in. There's no a priori knowledge required, to deploy this. So what happens is, on a very big level, the data packet is forced to take multiple paths from the DU to the RU through multiple switching layers, right? And through all these strips, it kind of records, what combination matched the latency requirement for the RU, right? And that combination finally gets a high reward for this entire episode. So one journey from DU to the RU is one episode, and the reward associated with that episode is whether I was able to meet the latency requirement for that RU for that particular profile. right? So that's the big picture of our reinforcement learning algorithm. On a more detailed scale, we deploy what is known as Q learning, right? Which tells a data packet at a certain state what is the best action to take from here. So in our case, the action would just be the next switch that it has to connect to, so that it can actually meet the end-to-end latency requirement. Now the problem here is so this by itself is actually very basic ML, right? But where the challenge will start happening is that once you want to manage 20,000 different profiles, right, and then the switches will scale up proportionately, all of a sudden your state space will blow up, right? You will have thousands of state space variables, and this will actually make just conventional Q learning very non-practical, because the matrix that is required, so basically Q matrix would actually give you at what state the best action is to be taken, right? So this would blow up, and this would actually not be realizable. And so this is where an innovation which has recently been explored in the ML space, which is called the deep Q learning. This is what we have leveraged to solve this problem, where we are using a neural network itself to predict the next action for a particular state, right? So the details can be discussed in a one-on-one call if required, but on a very big level, we are using an ANN which tells the network for a particular state what is the best action to take. Now the training gets carried on with multiple episodes. So you saw a specific training table which was shown in the previous slide, right? So it goes through all of them, and it goes through all of these switches, and kind of records for every combination whether it was able to meet the relay requirement or not. And with that, it has a certain Q data set with it, which tells that for this state, this is the switch I should connect to. And so finally, once the training process is done and we come to the actual deployment, it's pretty straightforward, right? For a certain state, it looks at the Q table, which is now represented by an ANN, and says, well, okay, I am at this state. With this state, this particular switch gets the maximum Q value. And so I'm just going to connect to that switch. So at the end of the day, it's just a single click deployment for the operator once the model is trained. It just has to give, the system would just take the new RU data set into account. We just have to upload the new RU data set into the system, and that's it. Our RL framework will directly tell the operator, connect to switch 4 of layer 1, then you connect to switch 2 of layer 2, and then you're connected to the RU, and this will meet our latency requirement. So that's the end-to-end vision for our approach. Yeah, the next slide will actually show some representative results. Can you go to the next slide? Yes. So just for this webinar, we have simplified the use case. So you can see there are 3 layers. Layer 1 has 1 switch, layer 2 has 2 switch, and layer 3 has 4 switches. Right. And so here, basically what is happening is that we actually have each layer, we are assuming that the latency of each layer is the same, right? So basically, whether it connects to switch 2 of layer 2 or switch 3 of layer 2, it would face the same latency. However, what is also important for us is the load that every switch gets, correct? So it's just because the 2 switches in layer 2 have the same latency, it does not mean that all the connections should just route it to 1 switch, and then the other switch would be totally empty. Right? That's not efficient utilization of resources. So we imbibe that also into our code, and we say that, okay, just because 1 switch meets all the latency requirements, we cannot route all the data through that switch, right? So that's an additional constraint that we are working with in our deployment. Okay. So now here you can see that with this switch structure, if you just connect a new RU, it's already been trained by all the RUs, like you saw in the previous slide, right? And now we bring in a new RU. And so now if you look at the top plot, the blue plot, actually the blue curve actually shows the minimum latency requirement, and the red curve actually shows the maximum latency requirement. And then the yellow curve sitting in between actually shows the predicted latency that the packet faced on its journey from DU to RU through multiple switches in between. Now, the expectation obviously is that we should always lie somewhere in between the blue and the red curve. And you can see for the most part, we've been actually able to meet that requirement. There are only some specific RUs for which we are marginally off the spec. But overall, the accuracy is very high for the current implementation. Also of importance is the plot below, where you can see that I've numbered the switches from 0 to from 1 to 7. So there are 7 switches in this thing. And when I say 0, it's actually a direct connection from DU to RU, right? And you can see here that there is an overall a reasonable spread in the switch number that is used. Right? It's not as if just because, let's say, switch number 5 meets the delay requirement for almost all packets, I'm routing it through switch 5. So we are actually avoiding that loophole also in our algorithm. So it actually ensures efficient resource utilization. So this is just a snapshot result. We've actually had some very exciting developments within our company to to ingest multiple things and even program the route and the switch connections on a layer level. So at every layer, we have developed algorithms where the connection between every layer can get optimized, right? So let's say layer 1 has 1 switch, layer 2 has 2 switches. Let's say each switch has 2-3 ports. How do these ports kind of work together? So we are looking into all of these minute detail level implementations in our company. With that, I go to the next slide. And so from an ML standpoint, we have to work a lot more, to imbibe hybrid nature of data, not just latency, but it could be, it could be, let's say, the optical fiber length, it could be latency, it could be bandwidth, it could be so many other things that the network can provide to us. Finally, as I think everybody appreciates, the data becomes the king. The more data we are able to get from operators, the more we can train our model so that we can reduce the workload of the operator. And finally, we also want to go towards graph neural network for better, for better extension of our ML algorithm and improve our algorithm further. So with that, I conclude this the RL part of our talk, and I give it back to the Delat team to take over.
Yeah, thank you, Vignesh. And just at time, Hari and Arunesh, if you want to maybe take 2 minutes to talk about company overview, and then we can go back to the Q&A. So, and for audience, actually, if you have any questions, please drop a question in Q&A. So we'll try to answer those here.
Yeah, sure. Rajesh, I'll talk about a lot. I just want to quickly introduce who we are, what we do. Now, we started in 2017, relatively young company. We hit our growth spurt sometime in 2021. Ironically, we have to thank COVID. Um, you know, that has actually, transformed us from single project focused on one customer to diverse, we do many things today, not just services, but also R&D. So in the service space, we have RF and antenna engineering right at the top. And then we do system engineering, embedded, and also we have services for platform designs in the consumer electronics, specifically, say PCB board design for glasses or any of the RL devices, and we have a global footprint. So we are primarily based in US and Canada. We have footprint in Europe and also Asia. And we are figuring it out how to actually transform our newfound energy. We are young, youthful. So with that, I hand over to Arnish.
Hey, thanks, Ari. ACL Digital, most of you would be knowing, but a brief about us. We are part of Alten Group, headquartered in Paris. We are a premier engineering services company with nearly around 57,000 people worldwide and a presence in 30 plus countries. And we have been fairly in all the domains: automotive, aerospace, banking, finance, healthcare, retail. ACL Digital is a digital arm of Alten, and we serve customers, mostly Fortune 500 customers across the globe. And our services include typically all the way from the chip to cloud. We work with key customers in the semiconductor world that you can see around today, and all the way to the cloud data center companies and all the verticals. In fact, a couple of the customers that you see today are marquee customers that we can anyway pinpoint. And telecom is one of our core areas, and that's where we felt that with our exposure with operators and OEMs worldwide, AML can be a good story, and that's where our partnership goes in. And our services offerings primarily goes all the way from the product development, re-engineering, sustenance, deployment, and managed services. So pretty much there in all the services on the telecom side. With this, I think we can get into the Q&A.
Hey, Naina, can you open up the bridge? I think there's some people, I think you may have questions online. I think I see Prasad Roy from audience. If you can enable the bridge. In meantime, while Naina is trying to figure that out, I think there are some questions on the Q&A. I think the first one, are you using external LLM models for training or in-house AI? Vignesh, you want to take that?
Yes, sure. So we actually are currently fully developing it in-house. So the deep Q learning model and all the fundamentals is just being worked up from scratch. So
thank you. I think the second one, what are some of the real world deployments of Open Fronthaul, and what lessons have we been learned? Maybe Ganesh, you want to take that?
Sure, Rajesh. I think from a fundamental point of view, it is a combination of three different domains: the RAN domain, transport, and timing. So the combination of these three factors, or the domain expertise required across these three, brings its own unique set of challenges in deploying Fronthaul, especially when you start scaling it for hundreds and thousands of RUs across various cell sites, and when you try to centralize and additionally when you virtualize the RAN, right? So to maintain the levels of latency that is required and to service all the users with the throughput and QoS, make sure that all of this is addressed, we do have unique challenges. And additionally, if you add more factors like having resiliency and load balancing, you need to manage this whole fronthaul network in a very intelligent way, dynamic way, adjusting to the conditions. There could be fronthaul network impairments, timing related issues. Sometimes there could be a drift or something, and the worst case could be a loss of sync. How do you take corrective and preventive actions dynamically while managing this fronthaul network? That is the thing that is bothering the folks that are deploying, the operators that are deploying large scale networks. So the traditional network deployments have been very, very fixed, all pre-configured and with fixed parameters. You don't change anything, but we are moving towards a more dynamic network, and the fronthaul network is going to evolve and transform into something like your data network, where the seamless number of routers connect to each other, routing algorithms work. And Hari made a reference to the data center analogy there in terms of your total compute power required and saving energy, reducing the cost of operations. All these things bring an element of a feeling of getting overwhelmed. So you need the assistance of some systems, some artificial intelligence and machine learning to assist those who are operating the network today.
Thank you, Balaji. Thank you, Ganesh. Next question is on how will the Open Fronthaul evolve with the transition from 5G to 6G? I know this might be good for Balaji to take it.
Yeah, sure. Thank you, Rajesh. So I think some key aspects will emerge as we move towards 6G. On the one hand, we do see ML and AI, as we have seen in this presentation, pervade more and more aspects of the RAN. And there is already a provision in the current O-RAN spec with respect to RIC, but there is more and more functional disaggregation and even moving AI further to the edge that's being talked about. So this may bring about even new interfaces or new sort of disaggregated modules in 6G, maybe even closer to the RU. There is already talk of one that is inside the DU to do with very, very time-sensitive tasks like scheduling. Then the notion of spectrum sharing and dynamic mechanisms for that is becoming one of the main themes for moving from 5G into 6G. So you may have heard about MRSS, right, multi-rat spectrum sharing, and whether again what does that imply from a point of view of the front haul interface, the management interfaces, and maybe further use of ML for spectrum sharing. These are all areas that will impact the specification. There are some new, not necessarily 6G, but there are some new emerging technologies such as radio over fiber, PON, and so on. So there is even a notion of an open optical front haul, and we'll see where this goes. Maybe that kind of seeps into O-RAN and has an impact there. And finally, I would say specifically from a front haul point of view, security has been a paramount concern, and there is a feeling that not enough has been done at the moment to address it, and that will be especially with the challenges of AI and data poisoning and data spoofing and those kinds of possible attacks. I think that will become a very, very key aspect. So I think these are some of the salient things that come to mind. But 6G is very new, and there may be new twists around the corner we don't know about. So yeah.
Yeah, thank you, Balaji. I think we can take maybe one or two questions. I think one question is: is the model currently trained for delay-related parameters only, or is it generic? Can be trained to determine the base connections based on the other factor as per requirements? Yeah, Vignesh, you want to take it?
Yes, sure. So thank you for the question. The whole point of using deep Q learning is that we can actually extend the state space by a lot. So the state doesn't just have to be delay. It can actually be a myriad of different parameters depending on what the network demands. So just using traditional Q learning, it will fault there because the state space will become so high that the matrix will be unmanageable to process. But the whole point of combining this ANN with Q learning gives us that flexibility that we can take a lot of parameters and make the state space have thousands of different variables and tie it to a reward function so that it optimizes several different parameters in its connection from D to I.
Thank you, Vignesh. I think there is one last, maybe one or two question we can take. I think one question is: how does the platform fits into the O-RAN architecture with SMO and the RIC framework? I can take it. Maybe Hari, you can add more if you like. Uh, I think this is a very good question. I think, and we don't want to introduce any new network functions because that create more bottlenecks with interoperability. So the work we are doing in ML space actually it aligns with. We want to align with the O-RAN AI ML framework, and we plan to integrate these functions within the SMO layer. We are still in early development, but our goal is to address the deployment challenges using automation tools with some kind of SMO layer, correct? So for both CUDUs and also from the RU point of view. So, but yeah, whatever work we are doing, I think it aligns with the O-RAN SMO framework and AIML framework.
I guess I want to just add the E2 interface aspect to it. It's more of a, ability to convert any of data collection entity to exchange or provide the collected or learnings, back to the central management agent. Right? that is where I think the standardization, open APIs will play a big role. Like independent players can come up with different models they can deploy, and then learnings could be backfed to a central agent. They can become like a global models for everyone's use.
Yeah, thanks, Rajesh, and thanks everyone for taking your time off to be part of this webinar. And we will be continuing this webinar as we make progress in our overall development, and we'll come with top updates and every quarter. Look forward to see you more often in our webinars. And if you have any questions, please do reach out. This recordings will be shared over the LinkedIn, other social media posts. And you can also reach out to us offline, and you can ping us in any of our LinkedIn profiles. Thanks to our distinguished speakers, panelists, and everyone in the call today. And have a great day.